She really likes to yell into that speaker. Man, it's so loud. Find it yet? It's in there. I'm not sure how it's expressed. Probably expressed with a bunch of summations. At least two. One in the numerator, one in the denominator. Now, if you have been paying attention in your math classes for the last, let's go 4 years, this should look familiar, but they would never have written it like this in your math class, because what you're looking at is a weighted average. That's what it is. You'll notice that it sums over m in the denominator, dividing by the number of things, and the top is giving weight to each of the things. In this case, R is there's an R or X? In this case, X is the weighting part, and M is the number, the object. It's a weighted average. So if you found it on your equation sheet, it looks something like this. X, center of mass, equals the sum over I of Mi times Xi over the sum over Mi. You're summing over the number of individual objects. First thing I want you to put in your notes. The center of mass is a location. It's a place. It's not a mass. It's where something is. The center of mass represents where the average mass of the system is. So you should understand that for a three-dimensional object, there's XCM, YCM, and ZCM. That you'd actually have to sum this in 3 dimensions if you wanted to find the actual center of mass of our system. Now, for the most part, we tend to think of our objects as having a center of mass that's in the middle. But that doesn't work if your object is asymmetrical, or if it's got, let's face it. You guys told me that one of the missing menu items was mashed potatoes. I'm okay with mashed potatoes, but I think if there's stuffing, you don't need mashed potatoes. I would argue that mashed potatoes are creamy. Uniform consistency. If I make a cube of mashed potatoes, it is likely that the center of mass is in the middle. But stuffing is not like that. It's got bits of this in it and bits of that in it. The density is not symmetrical, which means if I make a cube of stuffing, I don't know if the center of mass would be at the middle. There might be denser areas on one side than the other, which would shift where the center of mass is. The center of mass has to take into account the asymmetry of the density of your object or objects. So when we talk about center of mass, that's what this is calculating. In fact, the real definition or equation for center of mass is much more difficult for you guys to tolerate. Because it should be an integral, a summation over an object, summing the infinitesimally small pieces of mass and how far away they are from each other. That's how we determine the center of mass. I put an R here because the truth is, I don't want to be held to X. I want you to realize that you'd have to do this in the X, Y, and Z dimension. So I'm going to use R as a general placeholder for where the center of mass is, and I mean the vector R. 3-dimensional location in space. Now, a couple of big things about the center of mass, because what it really is, it's the balance point. If I was to put an object on a pin at its center of mass, the object will balance with equal amounts of mass in all directions around this balance point. Does that make sense? So if you put something at its center of mass, it should balance. Often, the word center of mass can be replaced with center of gravity. They technically aren't the same. The center of gravity is the location upon which gravity would act on an object, should it be in a gravitational field. But this object doesn't have a center of gravity if it's not in a gravitational field. But it always has a center of mass. Also, there are some technical differences between center of gravity and center of mass that don't matter in this class. But I want you to understand that they, on the test, will interchange center of gravity and center of mass, but they are not the same thing. For our purposes in a gravitational field, we will treat them as though they are the same, but they're not. I will say, ultimately, gravity acts over all of your body, but in calculating torque or other things that involve gravity, more technically, you would use the center of gravity for the calculation as the location upon which gravity acts on an object. That way, if you are looking at an object that might tip over due to a gravitational force and other forces acting, you would use what's known as the center of gravity in that calculation. Use it in planes too all the time in calculating the way in which they perform in the air. So we will use the words interchangeably. I will never say center of gravity, I don't think, hardly at all. I think I'm pretty much in my vocabulary, center of mass is what I use. So what I would like to do real quick is take a moment and show you how to calculate center of mass. We're going to do a very straightforward example. I'm going to give you a series of steps on how to calculate center of mass, and I'm going to then follow it up with saying you will never have to do this on the exam. They never ask it like this. They're going to ask about center of mass, but they're not going to ask it for a static object. We will need to calculate center of mass next semester when we're dealing with orbits, and we have to find the center of mass of perhaps a planetary system, because orbits tend to go about the center of mass of a system. In the same way that, and I'm going to say this to you guys just so you understand, if you throw an object into the air, an object will naturally pivot about its center of mass. You do need to know that. So like if you throw something and there's no established pivot point, it naturally pivots about its center of mass.
Does that just mean that it spins?
Yes, but I mean, if you talk about like a car going off a cliff, it's going to spin. What does it spin about? It spins about its center of mass, wherever that happens to be in the car. So, stunt drivers will adjust the center of mass to adjust the pivot point. All right, so let's deal with this for a bit. I want to create 3 random objects, and we're going to talk about this in a one-dimensional fashion. So I figure one dimension is probably good enough to get us started. So of those 3 objects, I'm going to have just 3 things kind of light up on a number line. And let's get some masses up here for these objects. Let's say 15 kilograms. Let's go 5 kilograms and 10 kilograms. And let's say that this is, let's go with 4 meters and 5 meters. Tell you what, just because I'm feeling a little frisky, switch those. Mostly because I want you to be able to determine an obvious location for where the center of mass is. Where do we expect the center of mass? A, B, C, or D? Where do you think the center of mass of the system is more likely to be? Raise your hand if you think A, B, C, D. I think it's probably going to be B as well. I have a heavier object located further away from the middle of the system. The middle is not the center of mass. The middle is here-ish. Maybe here-ish. It's hard to know where the middle is. If I take the whole distance divided in half, I guess the middle is 4.5 meters from one side. The first thing we have to establish in dealing with any center of mass problem is a point of reference. We are measuring a location. Because we're measuring a location, that location is given from a point of reference. Any place can be our point of reference for the center of mass, but we have to communicate and establish a known point of reference, a known location that we will call 0. I'm going to tell you from the beginning, it will always be easier to take one of your objects as your 0. Always. So I would encourage you to pick one of your objects as your point of reference. I'm going to force us on purpose to use this point as 0. And the reason is I want you to understand that the center of mass is a vector quantity. And therefore, any distance that's to the left of this 0 has got to be negative, and any distance to the right of this 0 has to be positive. And you can reverse that, of course. But what I mean to say is that when you choose your reference point, you are also picking positive and negative directions based on your reference point. Now, actually calculating the center of mass is really easy to do. We're going to take and sum every mass and its location from the reference point. And we're going to divide it by just the sum of all the masses. It's not hard to do once you realize what you're doing. This is going to give us our location to the center of mass. So I have a 15 kilogram mass, a 5 kilogram mass, and a 10 kilogram mass. I'm going to add up m times x for each of the masses. But the denominator is just the sum of them all. So 15 plus 5 plus 10, or 30 kilograms. So putting in my values for my location, the 15 mass is located -5 meters away from reference. The 5 kilogram is located at the reference point. The 10 kilogram mass is located +4 meters away from the reference point. 5 times 15, 75. 10 times 4, 40. So -75 and 40, -35. So my answer is -35 over 30. This is meter kilograms divided by kilograms, so my answer is in meters. And our answer is pretty straightforward here. I'm going to divide both of those by what? 5 and get 7/6. So my center of mass is located a distance 7/6 meters from the reference point. If I was to put this on a teeter-totter, it would balance right there. Now, the thing about the center of mass is the center of mass is a fixed location here. It shouldn't matter what our reference point is, meaning it should always work out to be that location. It's not 7/6, it's this place. So no matter where I choose my reference point to be, I should get the same answer. Prove it to be true. I've given you a new reference point. It shouldn't be a surprise of what our answer is going to be. See if you get the same answer, the same location. I mean, it should be 3 5/6 away based on my rudimentary math skills. Well, maybe not 3. Maybe 5 5/6 away. I don't know. It's fractions. It's hard. Big math. Well, it's got to work, but yay. I'm glad you got it to work. Let's see, that's 65. That's 175 over 30. I got 5 5/6. Is that what you got? Again, it's a place. Now, this is not how it's going to be on the exam. If it is, it's usually only going to be 2 objects. But what we have to be prepared to deal with is that they don't want generally for us to have calculations of the center of mass. They're going to have these objects moving. And then they're going to want to ask us questions about what is the velocity of the center of mass of our system. Meaning, we'll have to find a way to take the derivative of this with respect to time and look at the rate of change of the center of mass of our system. That's where this is going to go. So although I'm going to give you homeworks with some basic center of mass calculations, it's not always going to be about calculating the center of mass in this way. Now, let me pause here for a minute and just for, just to make sure we are in the same place. This was a one-dimensional question. It's not hard to create a two-dimensional question from this. And so I want you to start recognizing that a two-dimensional problem is more complicated in that it will be in two dimensions. You're still breaking up your problem into X directions and Y directions. So one thing that they've done in the past is they've had something like, this would mostly be on this would be like on a multiple choice. They'll have like a square like this, and they'll say something like, in this square, the center of mass is at its middle. But then somebody comes and breaks a piece off of the square. How does that shift the center of mass? And they'll ask questions regarding something like this. Well, this is clearly affected. This has clearly affected both dimensions a small amount, but one dimension more than the other. So these kinds of questions are multiple choice style questions, and we have seen those in the past. All right, folks, that's it for today. That was a lot of fun. I enjoyed it immensely, especially the quiz part. Boy, I love a good solid quiz. I know you feel differently about it. Tomorrow we're going to try again. We're going to try again. It'll be fun. I've got a good idea for tomorrow. Yeah, good idea for tomorrow. It'll probably bring you pain and consternation, but that's what I live for. So, any questions, the guys at home? All right, guys, have a great day at home.